Hi, it's Mr. Doro. Today I'm going to introduce the VSEPR theory to you, and we're going to use that to determine the shapes of molecules. So get ready. Well, first of all, we have to know what VSEPR stands for. I know it's spelled like VSEPR, but it's so much easier to say VSEPR, so that's what I say each time. Here's what they stand for. This is an acronym. The V stands for valence, the S stands for shell, the E stands for electron, the P is pair, and the R is repulsion. So what this is all about is the outermost electrons, the valence shell electrons, and how the pairs repel each other, and that determines the shape of the molecule. Now you will have to know what each of those stand for, so why don't you go ahead and start memorizing it right now. Another important thing that you have to know is why the electrons arrange themselves the way they do. It's always about the central atom that we're talking about after we draw a structure, and the reason that they do it is in order to obtain two things. One of those things is maximum separation. They want to get as far apart from each other as they possibly can. The other one is minimum repulsion. When they're further away from each other, they don't repel each other so much, and so they'll arrange themselves in the way that they're farthest apart and repelling each other the least. There really are just three steps that we need to know for VSEPR. The first one is to draw the electron's dot structure, and this is for covalent compounds only. If you don't know how to draw the electron dot structure, then you need to stop this video right now and go back to the one that's called molecular structures. That goes through how to do the electron dot structure. And then we're looking at the central atom, and we want to find the number of bonding and non-bonding sites around the central atom. That means how many bonding areas, things it's bond to, or how many dots that it has on it. And then once we do that, we just determine the molecular geometry from those domains around the central atom. It's pretty simple once we get going. Our first example is Cl2. And you can see that I've drawn the electron dot structure for Cl2 here. Now the thing is, anytime you only have two elements, then it is going to be the same shape. And the shape is going to be linear. I've got the molecules, the ball and stick molecule that we built in lab right here for Cl2, and you can see that this is straight across, but I also have a balloon here because I want to show you how this is going to work. The balloon area inside the balloon is going to be an area where the electrons are being shared. On the ends of the balloon, like down here, and this other end right here, that is where the atoms would be. That'd be like these green spheres. And so as you go across, you can see that this makes a linear shape. So the shape of this is going to be linear, and that's going to happen anytime you only have two atoms. Our second example is SiO2, and I have that one drawn here also, the electron dot structure. If we were to build this in the lab, then this is what it would look like right over here on this picture, and it would have two double bonds, and it would be straight across as you can see it. So the bonding domains, that's something that we need to talk about right now. The number of bonding domains, and that says number, that's not hashtag, that's number of bonding domains around the central atom. This is our central atom, the Si, and so we're just looking for how many bonding areas, whether it's a single bond or a double bond or a triple bond, it doesn't really matter. This is one bonding domain, and this is another bonding domain. So the number of bonding domains is two total bonding domains, or bonding areas, or bonding regions. The number of non-bonding domains is, I'm looking for dots. Are there any dot sections, or lone pairs, or unshared pairs on the central atom? This has none, so our number of non-bonding domains is 0. And our shape, as you can see right here, looking up at this one, that it is straight across from each other. Now the reason we use the balloons a lot of times, and why I'm showing you pictures of the balloons, is because they will naturally take the place where they do get maximum separation and minimum repulsion. So if we look at this and can visualize it, we have an oxygen on one end and oxygen on the other end, and our central atom is right there where they're tied together, and this makes a linear shape. So the shape for any time you have two bonding domains and zero non-bonding domains is going to be linear. It doesn't matter what the molecule is. If it's 2 and 0, it'll be linear. For our next example of SeO3, I've got the electron dot structure there, and you can see I built a molecule right up here in the corner, and this molecule has the double bond and two single bonds. It's all on one plane. They're all laying flat, and so it kind of makes a triangle right here. And so in this central atom, the selenium, is still in that plane also. Same thing with the balloons. These balloons are all, here's where the selenium would be, and then here is where the oxygens would be, and they make a triangle also, and that middle atom is right in that plane. The number of bonding domains for this, looking around the central atom only, is 3. The number of non-bonding domains, there are no dot dots on the central atom, so that's 0. And this shape is called trigonal. That's because it's a triangle. Trigonal, planar. The planar means that they're all on one flat plane. They'll lay flat in there. So anytime you have 3 bonding and 0 non-bonding, that shape is going to be trigonal planar. Our next example is CBr4, and you can see that around this central atom on this one, there are 4 things bonded to it, so that is 4 bonding domains. There are no dot dots on the central atom, so again we have 0 non-bonding domains. You take a look at the ball and stick model. This is the one that maybe you had a little trouble drawing in the model building lab, but you can see that this central one is lifted up a little bit further. But if we look at just these corners, then we can see that there are 4 faces that this has, and that 4 faces is called a special word called tetra, which means 4. Tetrahedral, H-E-D-R-A-L. Tetrahedral means 4 faces. This balloon model has the same thing. You can see that right here in the center, this is raised up a little bit, and if we looked at this, there would be 4 equal faces of kind of like triangle shape if you looked at the bottom and the other side right there. So anytime you have 4 bonding and 0 non-bonding, it's going to be tetrahedral. Okay, for this example, we finally get a dot dot on the central atom. So for PF3, you look at the electron dot structure, you see that it's bonded, the central atom is bonded to 3 things. So our bonding domains or bonding areas is 3. And then we have this dot dot right up here. That dot dot counts as 1 non-bonding region or 1 non-bonding domain. And so I've got the ball and stick model for this one. And you can see that we don't have anything located right up here. That's because that's where that electron, those unshared electrons are. And that's the same thing for our balloon model. And so that's not eyes on there, although that does look a little bit scary. But that white balloon represents the non-bonding region or non-bonding domain. And what that does is that pushes these other molecules or these other atoms, it pushes them down because you have this also repelling and pushing those down. Now it looks like a guy with a mustache on there and something wrong with his hair. But this shape would be called, there is a triangle on the bottom, a triangle base, and it comes up to a point in the center. And so that shape, here's the triangle base, and it comes up to a point, and that shape then is called trigonal because of the triangle base. Trigonal, another trigonal, but this one's not planar, this one is pyramidal. That center point is raised up, pyramidal, like a triangle base pyramid. Trigonal pyramidal. Anytime you have 3 and 1, 3 bonding, 1 non-bonding, trigonal pyramidal. Okay, for H2SE, we're looking at the central atom. We have our bonding domains, 2, and we have our non-bonding domains, also 2. This would be the ball and stick model right up here, and you can see what the shape looks like. It's all laying flat on the table, and this is what that ball and stick model does not show are these electrons that are right up here. Draw those in pink. Those unshared pairs of electrons that are the white balloons. And so if we look at the shape on that, on the red balloons make the shape. The white balloons influence the shape because they push these down away from each other. They're repelling and pushing these other ones down further away, or these electron pairs is really what they're pushing. So that shape really is just called bent. If you have 2 and 2, 2 bonding, 2 non-bonding, then that's going to be a bent shape. Here are some more for you to look at. I don't have an electron dot structure to show you on this, but we can figure it out just from the balloon structure. Remember, the red areas represent bonding domains, and the white areas represent non-bonding domains. So looking at this, we have 2 red balloons, and so those 2 red balloons are going to be 2 bonding domains, and 1 white balloon, that's 1 non-bonding domain. And if we look at this, the central atom would be right here, the other atoms are here, and this is the molecular geometry. The molecular geometry is also called the shape. This is also a bent. It's just bent at a different angle than the other bent that we had. We could also determine the electron pair geometry, and if we were looking at the electron pair geometry, we would just be looking at all of the electron domains, bonding and non-bonding together. And then the bottom one down here, this has, I don't know if you can see it or not, but right in here would be your central atom, and this has 1, 2, 3, 4, 5, 6 balloons. So this all red balloons, 6 bonding and 0 non-bonding. This kind of has a special name. If you look at it, it kind of makes a square right here. Those 4 do, and then it has like another one shooting straight through it. And so if you broke that down, that would make on that 8 equal faces, which would be called octahedral. Anytime you have 6 and 0, it's going to be called octahedral. Okay, one of our last ones is this one up on the top, and this has 5 balloons, 5 red balloons, which means it has 5 bonding domains, and so we're going to put 5 here. It has no white balloons, so that's 0 non-bonding domains. And this one you got to use your imagination a little bit. You got to look at it on 2 planes. This plane right here of those 3 balloons, and then this balloon going straight through. It's kind of like a harpoon going straight through it. So it's like a triangle with a harpoon going straight through it. So that's called trigonal because of the triangle. Trigonal. And then it would be like a pyramid on top and a pyramid on bottom if it went up to the points. So it's trigonal bipyramidal. 2 pyramids. 2 triangle-shaped pyramids, or triangle-based pyramids. Look at this one down here on the bottom, and notice that we have 3 non-bonding domains and only 1 bonding domain right here. So remember, when we're talking about the molecular geometry, the shape of this, then we're only really looking at the red balloons. The white balloons affect the shape, but the red balloons are what tell us the shape. So if these are our 2 atoms, our central atom and our outside atom, then you look at the shape right there, that shape is going to be linear because there's only 2 atoms. And so these here affect the shape, but they don't take part of the shape. And finally, here's a variety of different things. You have electron dot structures and balloon structures and models and number of bonding and non-bonding domains. And you should be able to tell me what the shape or the molecular geometry of each of these molecules are. And so make sure that you have these done. Remember that this is part of your grade to get these complete. Have a great day.